Our next topic is looking at the area of a region. So we're going to use the sum notation that we were looking at previously in order to try and find area. Okay, so what we're looking at on this first one, we're going to try and approximate the area of the region between the function f of x equals negative x squared plus 5 and the x-axis on the interval from 0 to 2. Okay. So the way that we're going to do this is we're going to use little rectangles and sort of break our graph up into these little rectangles in order to approximate the area. So what I'm going to do to start with is I'm going to go ahead and label out my x-axis here. And I want to split this up into 5 different intervals. So I'm going to go ahead and count my x-axis. If you think, 2 is our upper limit here. I'm going to divide that by 5. So I'm going to count my 0.4 on my scale. I have 0.4, 0.8, 1.2, 1.6, and 2. And I'm just sort of arbitrarily choosing here to break this up into 5. You could break it up into 10, you could break it up into 20, however many intervals you wanted. I'm just going with 5 on this one. Okay, so then we're going to plug each of these values into our f of x function. Okay. All right, so first, if we plug in, let me go ahead and actually label my y-axis here. Okay, so if we plug 0 into this function, we would get 5. So we start off with the point here at 0, 5. If we plug 0.4 into our function, we get 4.84, 0.4, 4.84. If we plug 0.8 into our function, we get 4.36. If we plug 1.2 into our function, we get 3.56. If we plug in 1.6, we get 2.44. And if we plug in 2, we get 1. Okay, and of course this is a parabola. It's going to pass through these points. Okay, so what we're going to do now is we're trying to approximate the area between this graph and the x-axis on the interval 0 to 2. So what I meant by I'm breaking this up into 5 different intervals is we're essentially going to think of this as 5 different rectangles, okay? Now this first one, we're going to use the right endpoint to draw in little rectangles. So this would be one little rectangle. This would be another little rectangle. And so on, using the right endpoint every time to make our little rectangles. Okay, I'm going to call these 1, 2, 3, 4, and 5. Okay, so to find the area or to approximate the area under this curve, we need to find the area of each of these little rectangles and then add them up. Okay, all right. So for number 1, area of a rectangle, of course, is just length times width. So our area here, each of these has a length of 0.4. And in this case, the width of this, or the height, whatever you want to call it, is this 4.84. Okay, so that would give us 1.936. All right, so for number 2, again, this right here is a distance of 0.4, and then this distance right here would be the 4.36. And that's going to give us 1.744. All right, third rectangle, we again have 0.4, and the height of that rectangle is 3.56. That gives us an area of 1.424. All right, fourth rectangle, again 0.4 on the bottom, and this one has a height of 2.44 for an area of 0.976. All right, and lastly, our fifth rectangle here, we again have 0.4 on the bottom, and then this one has a height of 1. So that's going to be an area of 0.4. All right, so if we take all 5 of those little rectangles and we add them all up, okay, so adding up all 5 of these areas that we just found, we get a total area of 6.48. Okay, now obviously if we look at what we just did here, we use these little rectangles to approximate the area under this curve. But for every one of these rectangles, we're missing a little space right here. There's a little extra space above our rectangle that we're not including in this estimation. So this is obviously not exact, and it's giving us an underestimation of the actual area. Okay, so that 6.48 is an underestimation of the actual area. Now another option would be to use the left endpoints to estimate this. So I'm again just going to sketch out this graph. I'm going to use the same 0.4 on my x-axis scale. All right, so our points that we found previously were 0, 5, 4, 4.84, 0.8, 4.36, 1.2, 3.56, 1.6, 2.44, and 2, 1. Okay, so same points that we found a minute ago. Okay, so this time, instead of drawing our little rectangles using the right endpoint, I'm going to use the left endpoint. And you can see in this case that all of our rectangles are a little bit above the graph of our function. Okay, so I'm going to call these again 1, 2, 3, 4, and 5. All right, so let's find all of our areas here. Okay, so number 1, we would have 0.4 times the height of this rectangle is 5, using that point right there. All right, so 0.4 times 5 would give us an area of 2. Second rectangle, we have 0.4 times the height of this one is 4.84, and that's 1.936. Third rectangle, 0.4 times a height on this one of 4.36. And that gives us 1.744. Fourth rectangle, 0.4 times 2.44. Right, and that would give us an area of 1.424. Shoot, I just realized I'm using the wrong point here. There we go. Sorry, I was looking at the wrong rectangle. Fourth rectangle has a height of 3.56. Sorry about that. So that would be 1.424. There we go. And then number 5 has a height of 2.44. And that one is 0.976. Okay. All right, so if we add up all 5 of these, we would end up getting 8.08. Now, of course, on this one, all 5 of our rectangles are a little bit above the graph, so this one would be an overestimation. Okay, so the actual area between our curve and the x-axis is going to fall somewhere between 6.48 and 8.08. Now, to figure out exactly what that area is, we're going to need some methods that are a little bit more precise. Now, in order to get a better approximation, we could use more rectangles. So instead of just using 5 rectangles, we could use 10 rectangles, we could use 20, we could use 100, or in order to think of this as finding the exact area, if we were to look at the limit as that number of rectangles approached infinity, we would be able to find the actual exact area under the curve. So our limits from unit 1 are coming back in. Okay, so to find the area, we're going to find the limit as n approaches infinity of the sum from I equals 1 to n of f of c plus I times delta x. Okay, now look at this graph down here to understand what all of this means. Okay, so we're looking at some function, this would be our f of x function, on the interval from a to b. Okay, and I'm saying that c sub I is just some point in this interval, and delta x is the width of the rectangle. Okay. All right. So we're basically looking at, we're taking the sum of all of these different little rectangles that have a width of delta x. Now our delta x is going to be the difference between the endpoints divided by n. And since we're looking at the limit as n approaches infinity, we're basically looking at the limit as our delta x approaches 0. So if we have these rectangles really small, then we'll be able to get a good approximation of the area under this curve. Okay, so let's look at a couple examples using this definition. All right, so our first one here, we're going to find the area of the region bounded by the graph of f of x equals x squared and the x-axis on the interval from 0 to 2. Okay, so instead of sketching it out and doing an approximation this time, we're going to use the limit definition. Okay, so what that tells us is that the area is going to be equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay, that's our limit definition of area. All right, now delta x is always going to be b minus a divided by n. In this case, that's 2 divided by n. All right, now the other thing here is the c sub I value. Okay, this is always going to be whatever we found as our delta x times I plus our a value. So in this case, our c sub I is equal to 2I over n plus our a value is 0, so I'm just going to leave that off. Okay, so let's go ahead and plug everything in here. So we're looking at the limit as n approaches infinity of the sum from I equals 1 to n of our f of c sub I. If we plug this c sub I into our f of x function, that would be 2I over n quantity squared, and then times delta x, that would be times 2 over n. Okay, now this guy right here, the 2 over n, since that doesn't have an I in it, and our summation is over I, we can actually pull that right out of the sum. Still has to stay inside the limit, but it can be out of the sum. All right, the other thing I'm going to do here is go ahead and square this, so distribute that through. So that would give us a 4I squared over n squared. All right, now once again, anything in here that doesn't have an I in it can be pulled outside. So the 4 can be pulled to the front, and the n squared can be pulled to the front as well. I'm going to make this the limit as n approaches infinity of 8 over n cubed times the sum from I equals 1 to n of I squared. All right, now you might remember from the previous video that the sum from I equals 1 to n of I squared is equal to n times the quantity n plus 1 times the quantity 2n plus 1 all over 6. So we can plug that in here now. This would be the limit as n approaches infinity of 8 over n cubed, and then all of this becomes n times n plus 1 times 2n plus 1 all over 6. All right, so now we need to simplify this a little bit before we can take our limit. So one thing I noticed here is we have an n here, we have an n cubed on the bottom, so I can cancel one of those and make that an n squared. Also, our 8 over 6 can be reduced to a 4 over 3. Okay, so I'm going to go ahead and rewrite this a little bit. The limit as n approaches infinity of 4 over 3n squared. Okay, now all of this we just need to FOIL out. That would be 2n squared plus 3n plus 1. All right, and then just distribute in that 4 over 3n squared. Yeah, distribute in that 4 over 3n squared. All right, so this would be 8 over 3 plus, this next term would be 4 over n, and then plus 4 over 3n squared. All right, so then lastly, to take our limit, okay, as n approaches infinity, both of these two terms on the end that have the n in the denominator are going to go to 0. And of course, this guy, 8 over 3, is just going to approach 8 over 3. So our final answer here is 8 over 3. All right, so this is how we'd use the limit definition to find the area under a curve. Let's go ahead and look at one more example. So find the area of the region bounded by the graph of f of x equals 3x minus 2 and the x-axis on the interval 2 to 5. All right, so once again, we are looking at our limit definition of area. So the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay, so our delta x is b minus a divided by n. That's 3 over n. And our c sub I is our delta x value times I plus our a value, which in this case is 2. All right, so plugging all that into our limit over here. Now the limit as n approaches infinity of the sum from I equals 1 to n, and then our f of c sub I would be 3 times 3i over n plus 2 minus 2 times our delta x, which is 3 over n. All right, now just like I did in the previous example, I'm going to go ahead and just pull this 3 over n out front because it doesn't have any i's in it. I'm just going to get it out of the way. And I'm also going to go ahead and distribute this 3 in here. That would give me a 9i over n, and then plus 6 minus 2. All right. So on this one, go ahead and just simplify this a little bit first. So that would be a 9i over n plus 4. Okay, so on this one, what we can do, because we have the sum of these two different things that are added together, I'm going to split this up into two different sums. All right, so with the first one, the 9 over n can be pulled out front with the 3 over n. So that would become 27 over n squared times the sum from I equals 1 to n of I. All right, and then for the second one, we'll just have 3 over n times the sum from I equals 1 to n of 4. All right, Now again, remembering those special sums that we saw in the previous video. The sum from I equals 1 to n of I is always equal to n times n plus 1 all over 2. And the sum from I equals 1 to n of a constant is always just equal to that constant times n. So in this case, 4 times n. All right, so in this first one right here, we have an n on top and an n squared on the bottom, so we can cancel one of those n's out. And then in our second term, we can also cancel that n out. I'm going to clean this up a little bit here. We would have 27n plus 27 divided by 2n, and then plus 12. All right, and then I'm going to split this guy up. So we would have the limit as n approaches infinity of 27 over 2 plus 27 over 2n plus 12. All right, so this term with the n in the denominator is going to go to 0, and then the other two are just going to be their values. So this would be 27 over 2 plus 0 plus 12, and 27 over 2 plus 12 is 25.5. So our area in this case is 25.5. All right, there is one more example of this if you look in the notes that I posted on Blackboard. So if you want a little bit more practice with it, go ahead and look at that. And of course, as always, do the homework and the labs on this section as well.